Hello, this video is entitled Conditional Probability, Section 3.2 in the Larson book, so let's see what this is all about here. A conditional probability of an event occurring means that another event has already occurred. Now, whether or not that other event will affect your probability, that's what we're going to get into here. But for example, let's look at the notation of this. That's the key. The conditional probability of event B occurring given that A occurred is denoted by this notation. Now, this vertical line is not really it's not a mathematical operator. It's not, it's not division. It's not anything like that. It's essentially, it's a vertical line that sort of represents the word given, or given that, or such that, or whatever. So that's all it is. A symbol represents words. So this says probability of B given that A occurred. So like it says here, probability of B given A. So when you reverse these around, they do make a difference. The probability, so they say probability of A given B occurs if it's written in this order. So it's not the same thing. So let's look at an example of rolling a single die, and in this particular example, with these events defined, I'll show you the difference between, in this case, why B given A and A given B would not be the same thing. So we have a single die with our six-sided sample space, and I'm defining A as the event of rolling an even number and B of rolling the number 2. So let's think about this. The probability of rolling B given A is the probability of rolling 2 given that an even number is rolled. So if we know that it's even, it effectively reduces our sample space down to 2, 4, or 6. If we know it's even, we're only choosing one of those, and therefore the probability of rolling a 2 out of just 2, 4, or 6 would be 1/3. So in other words, the probability of just rolling a 2 by itself would be out of all 6 of them would be 1 out of 6. But rolling a 2, given that you know it's even, is just 1 out of only these 3 numbers. Now let's look at the reverse of this, the probability of rolling of A given B. That's one you really don't need to do a calculation on or whatever once you kind of read this out and explain kind of what's happening here. This is now saying when you reverse it, what is the probability of rolling an even number given that you roll a 2? Well, if you know you've rolled a 2, the probability of rolling an even number is 1, meaning 100% chance it's going to be even if you already know it's a 2. So this example was just to kind of illustrate that, that you reverse those A's and B's or whatever letters you're using, and they're two completely different questions. Now, the idea of independent events. Basically, if the occurrence of one event does not affect the probability of the other event. So 2 events, A and B, would be independent if either one of these is true. The probability of B given that A occurred is exactly the same thing as just probability of B itself. Or if the probability of A given B occurred is just the probability of A itself, meaning that B had no effect on A, and the first one, A, had no effect on B. Events that are not independent are called dependent events, meaning the probability did depend on the other event. Like these 2 examples up here, they would definitely be dependent events. For example, the probability of B given A was 1/3, but the probability of just rolling a 2 would be 1 out of 6, and they don't equal each other. This one, the probability of rolling an even number, 2, 4, 6, would just be 3 out of 6, and that does not equal 1. So therefore, those are dependent events. Now, good examples of independent events are, well, I said rolling dice. It depends on how you're measuring them in conditional terms, but meaning it's what we expressed in the other example was a little bit different, but in general, coin flips, rolling a dice, for example, rolling a die, if you roll a 5, that's not going to affect what you roll the next time. In other words, basically, in other words, so the probability of rolling a 5 on the second roll, given that you rolled a 5 on the first roll, would be the exact same thing as just rolling a 5, because it would not have mattered that the 5 came on the first roll. Same thing with coin flips. It's coin flip, they're independent. Even if you flip the coin and you get heads 5 times in a row, that does not affect the next probability. It could be heads again, it could be tails, but it still has a 1 out of 2 probability. It's not affected by those earlier rolls. A roulette wheel, that's a wheel that has 38 equal spaces, usually contains. Some have 39, but that same kind of thing. You roll it, lands into a number, and then when you do it the next time they roll it and lands the number, it makes no difference what happened on the previous event. Now, drawing cards from a deck is interesting because that's only independent if you put the card back in there each time. In other words, if you draw a card first and you don't replace it, that's absolutely going to affect the probability of the next draw. If you didn't change you didn't put the card back, because now first of all you're drawing out of 51 cards instead of 52. I think we got an example of that coming up here, I believe. If not, yeah. So we'll see that coming up. Now, the probability of 2 events, A and B, occurring in sequence is the same thing. It's usually not this complicated, but the probability of A and B equals the probability of A times the probability of B that given A occurs. If they're independent, if they're dependent, this is true. If the probability of B, if A doesn't affect B, it would just be down here. It's just the probability of the two numbers multiplied together. So, for example, let me use that dice example I was using a minute ago with 1 die. What's the probability of rolling a 5 and then rolling a 5 again? Those are absolutely independent events because, like I said, it did not matter what happened on the first one. Well, the probability of rolling a 5 on the first one would be 1 out of 6. The probability of rolling a 5 on the second one would be 1 out of 6. So 1 out of 6 times 1 out of 6 would be 1 over 36. So 1 over 36 would be the probability of rolling back-to-back 5s. All right. Now, dependent events here for sure if you're not replacing the card. 2 cards drawn in succession without replacement. What is the probability that both cards are diamonds? Okay, so I'm labeling this as diamond on the first draw, diamond on the second draw. All right, probability of a diamond on the first draw would be 13 out of 52. Now, your diamond has now come out. So you've lost 1 total card, you're down to 51, but you've also lost a diamond, you're down to 12 diamonds. So that means in the conditional probability, the probability that you drew a diamond on the second one, given that you drew a diamond on the first one, means that probability is going to be 12 out of 51 because you're down to 51 cards and you only have 12 diamonds to choose from, so then you would multiply these two together. So now I'm saying, what if we replaced the card and made it independent events? Now I just wrote 1/4, 1/4, but that just basically means 13 out of 52 because that just reduces to 1/4. So essentially it's 13 out of 52, and if you replace the card, that means you have another probability of 13 out of 52 that you'll draw it on the second card. So you see, if it's replaced, it'll be the same probability, so you multiply those two together. And of course we get a different answer. So there's the difference, in the cards if you're replacing or not replacing. Now, how about this one? This is, I forgot to specify without replacement here. So let me fix that. I have now fixed the wording of the question to say without replacement. So that's exactly what I did in the calculation. So I have it in the next one. I don't know why I didn't have it there, but that's all right. It's fixed now. D1 I'm denoting as diamond on the first draw. H2 is heart on the second draw. So we're looking at two events, diamond 1 and heart 2. So diamond on the first and heart on the second. Now this is a dependent event. You don't have to really worry about the notation as long as you kind of understand where the numbers are. But this is, so it is P of D1 times the probability of heart 2 given we drew a diamond on the first one. So the probability of diamond on the first one, that's easy enough, 13 out of 52. That means we're pulled out a diamond, and there's now down to 51 cards. But unlike the problem we did up here with back-to-back diamonds, the difference now is if you're saying the probability of drawing a heart, yes, you're down to 51 cards, but all 13 hearts are there because we did not pull a heart on the first one. So it'd be 13 out of 52 times 13 out of 51. Whereas the other one, back-to-back diamonds, was 12 out of 51. All right. Next one, aces back-to-back without replacement. There are 4 aces in that deck. So you got 4 out of 52. We lose a card, so we know that goes down to 51, but we also lost an ace. So back-to-back ace. So 4 out of 52, we lose one, so now the next one will be 3 out of 51. So you just multiply those two together and you get 0.0045. Wonderful. Let's look at dies. Roll a single die 3 times. Find the probability that we roll exactly 3 5s. Oh, I did example with 2 5s earlier. I said it verbally. I didn't write it down, so that's good that this one is written down. So 1 out of 6 for the first 5. Doesn't matter. Doesn't affect the next one, which will be 1 out of 6. Times another 1 out of 6 makes 1 out of 216. Now, I'm writing, I guess actually I should have written this for the, let me move this down. Not that's that big of a deal, but actually this statement would make more sense if I put it below here, because it made it look like it was relating to the last problem, but this actually is relating to this one. Anyway, find the probability of that we roll at least 1 5. So I'm telling you something here. Didn't expect you to know this, but actually the complement rule. So you might think all is the opposite of none, but it's not. In this case, at least one. It's kind of like saying something is the opposite of nothing is one way to look at it, not all or nothing. So this is saying, so the probability of getting at least 1 is actually the complement of getting none. So in fact, you might get 1, 2, or 3 5s. That's the opposite of getting no 5s. So now that you know that, okay, I wouldn't expect you to know that. Now you know how to handle that anytime that you see this calculation. So now the no 5s we can get, so it's 1 minus, so the probability of not getting a 5 is 5 out of 6. Basically 1 minus 1 over 6. Everything 5 numbers in there that aren't a 5 times another 5 out of 6 times another 5 out of 6. So 1 minus this answer gives you then the probability you get at least 1 5 in there out of those 3 rolls. So you have a 91 over 216, which the calculator will make that 0.42. A little less than half, a little less than 50% chance. So here's a similar example to that. Probability a person in the U.S. has blood type O positive is 38%. 3 unrelated people in the U.S. are selected at random. Kind of important that they're unrelated, because obviously blood types can be affected by that. I don't know nearly as much science as you nursing majors do, but that much I do know. So anyway, probability that all 3 of them have 0 plus. They mentioned that because obviously that would be dependent, you know, on if they were related or not. Unrelated means independent probabilities. 0.38 times 0.38, 0.38, right in the calculator, no problem. I don't think I need to insult your intelligence by actually multiplying those in the calculator. This one says none have type. Now, okay, I'll put this in here at least for you. So if it's 38%, 38 probably 0.38 that they have it, yeah, I'm not saying you have to do this in your head. Not even this part. 1 minus 0.38. It's 0.62. So then you just say none have it would be 0.62 times 0.62 times 0.62 is 0.238. Then the probability of at least one is always, as I explained in the last example, is always 1 minus the probability of none. So you don't have to do anything other than go 1 minus the answer from part B. And there you have it. So we got to say there's a 76.2% chance that at least one person will have type O positive. Excellent. Now, conditional probabilities from row column tables. Example 7 here, nursing majors. So we have students enrolled at the OU Health Sciences Center. So it's broken down into males and females. So I'll explain how to read this here in a second. But I kind of am right now. But anyway, they're either nursing or non-nursing, and there's your total. So out of 37 students, 795 are nursing, and 2742 are some other health science major in that department. So these always add up, row and column add up down. And then we have 1,110 males, 2,427 females, so that adds down to give you the total number of students, and this adds across to give you the total number of students. So these are, you have column totals, row totals. Now the inside four numbers, those are actually and. They mean and something. You read it as and where the row meets the column. So this tells you that someone who's male and a nursing major means there's 95 of those students. Female and nursing, 700. Female and non-nursing, 1,015. Male non-nursing is 1015. Female non-nursing is 1727. Okay, so please forgive my flub there, but now we got it. So those are actually ands. Okay. So let's take a look at this. Find the probability that a student is a nursing major. So if you're just asking a probability of just a single item on here, it'll be divided by that 35-37. When we do conditional probabilities here in a minute, that's going to be a little different. It's not going to be divided by 35-37. So out of 35-37, how many of those are nursing majors? So you come down here, look at the column of the nursing majors, and that means you have, if you're selecting one at random, you're drawing a name out of a hat, whatever, 795 out of 37. Looks like I did them all. Well, you can't see I think this 2247 is the result from this one, but that's not, I don't know why I put that in there. I'm sure you would have had no problem putting those in the calculator, because like on a homework problem or a test problem, it's probably going to have decimal answers. It may have fraction on a test, but the homework's probably going to be decimal. But that's simple enough. Just divide it in the calculator and get the answer. And just make sure you check the rounding on whatever it tells you in the My Stat Lab there. Probability that the student you select is male. There are 1,110 males out of 35-37. So there's your fraction. 1110 out of 35-37. Now, C says the probability that a student is a nursing major given that the student is a male. Now, what that given does, it reduces our sample space. We don't deal with 35-37 anymore. If we know it's male, we know it's coming out of these 1110 right there. That's your denominator for this problem. It's out of the males. And then how many out of those males, we look across the row here, males are then broken down into nursing and non-nursing. It says this would be the nursing majors that are male, the male nursing majors out of the total males. So this will be 95 divided by 1110, and there we go. Now the next one, I'll leave that up here just for a second before I have to erase it. The next one says probability that a student is nursing and male. Now this is not conditional. This just means you just selected it. I mean, it doesn't say given that they're male. This says you just picked out a person who was a male nursing major out of the grand total. So watch what happens. This now becomes that same 95, because that means that's the number of male and nurse, but it's over the 35, 37. And I decided just for practice here that let's yeah, so I finished this, and like I said, we'll look in the homework here in a minute. I wanted to add some more parts to that same data, some more questions off that same data to especially give us practice on the conditional. So let's answer those 4 questions, and then we can move to the homework. Maybe I should have labeled these. Well, actually, I changed it to example 8, so I guess I don't have to go E, F, G, or whatever. So, probability that a selected student is male given that the student is a nursing major. Now, that may sound a lot like Part C, but it's not. It's the complete reverse. You see, this Part C says probability that they are a nursing major given that they're male. This says what's the probability of male given that it's a nursing major. So given that it's a nursing major tells us that the grand total, the denominator, comes from the nursing majors. Now, out of the nursing majors, 95 are male. Now, one thing, so you see it's 95 over 795, where it was 95 over 1110. So that was not, the numerator is not a coincidence, I'll tell you that. So either way that's worded, the top part was going to be the number of male nurses. It was going to be 95. But the difference you can see in the 2 answers is the denominator was different. But yes, the numerator was the same for both of them, and that would happen any one of these if you reverse them. It's going to be the top number is going to be the same. Let's see. And I can even take one of these other ones that I've got right here and reverse it and show you. What's the probability that a student is non-nursing major given that they are female? All right, given that they are female means we're only choosing out of the females. Right there. So I could change the colors, I guess, on these. I don't know if we need to or not, but there's your total, and then the non-nursing. So it's, wait. Oh, yeah, there we go. I was looking at the wrong one. There it is. 1727 divided by 2427. Now, I'll go ahead and reverse this one. I may not reverse the next 2, but I'll reverse this one. What if it said probability of female giving, they were not a nurse, non-nursing major. Female, non-nursing. So what's going to happen is, I mentioned that's, the 2 things you have there, that's going to be, the numerator value is going to be where these 2 intersect, no matter what order it's in. But if you go female first, so that green number stays the same. But watch what happens. You're now choosing out of the non-nursing majors, so that means this would change. The denominator now would be the 2742. It would still be 1727 on top, 2742 on bottom, if it was given that they were non-nursing. Probability of female, given that you know they're a non-nursing major. And there's 2742 non-nursings. It probably maybe take a little time to get the hang of this. Probability that they're female, given that they're nursing. So we only want to select from the nursing majors. Which is right here. There's 795 nursing majors. That will be our denominator. So you look up and down that column, and which one's nursing, how many of those are females? It's a number right above it. So it's going to be 700 out of 795. There it is. And then the last one, probability that you select a male, given that you know they are non-nursing. So the non-nursing will be my total. Yeah. Out of that non-nursing totals, oh, I guess I use it. Well, that's all right. I won't worry about my colors on this one. We'll just use green for both of them. Males, that's the male non-nurses are 1015 divided by the total number of males, which is 20. Total number of non-nursing majors. God, I said that wrong. I got it illustrated correctly, but total non-nursing majors is 2742, and out of those non-nursing majors, 1015 are males. There we go. So that concludes the lecture component here. Let's come over here and look at some. Oh, just in time, just to continue. All right, some of these conceptual ones. I'm going to skip ahead here and see what I think. Oh, we know this one. Oh, I already got the answer there. I guess you can take a look at that, can't you? Complement of at least one is none. So we've taught, yeah, you'd had no problem with that anyway. Do I have the same question twice? Well, okay. I'm going to go through and edit this homework. We're going to get rid of that. I'm going to pause the video. All right, I've deleted the repeat problem, and I'm glad I paused it and did that, because that would have thrown all the numbering off here. You know, when I started working problems, it would have been one number off from whatever I was showing. I want to do one when I read off those tables. Let's see. This could be a good one. Let me just look. Just go looking through. I'll find one here in a minute. Let's see. It's probably similar. I'll probably leave that one alone. That one doesn't look like it's too bad. Independent. Yeah, we could do the card problem. We'll come back to that. Let me just go back and. So number 4, I think, is the one I wanted. Number 7 for sure. Or 3, I think it was. Either one. Whatever. Let me bring up. Yeah, here we go. I'll put this in Excel, even though we're not using any fancy Excel commands to do anything here. I'll just probably be using Excel as a calculator, sort of like I did for that example right there from the last section. All right, now we got to see what the question says. I wonder why it didn't give me the totals. We can sum them up and get them. I thought I saw the totals in the question, unless I'm wrong. But you see, you can auto sum and get them back there. There we go. Give it a little room there so we can get where we got our totals. So let's see what we got here. All right, I want to center these. Okay. I could label those total, but I think you're good. I think you realize what we're doing. Yeah, the totals were there. Are they the same numbers as mine? Yeah. So I'll click done there. Find the probability that a student selected as male given that the student received a business degree. So I'm going to use color coding here on this one. So business degree, right there. Male, and make that a different color. From the business degrees, we have male, right there. So I'm just going to just anywhere, I'll just pick a cell right down here, and I mean, if you just prefer to stick this in a calculator, that really makes no difference. Divided by, I could have written a command, couldn't I? What am I doing? I could have just said, well, either way, you see what I was doing there, but I could go B2 divided by B4. But it wasn't wrong to type the numbers either. All right, let's see what it wants, decimal wise. It wants 3. I like 549. Wonderful. Probability receives a business degree given that the student is female. Given that they're female. So I'm going to focus on that part first. I guess I think I can choose no fill and get rid of those. I don't want to start putting too many colors in there. So now we'll go back and there's the female. Oh, is it back on no fill? Oh yeah, I gotta pick a color, I guess. There we go. Those are total females, given that they're female. I believe it said business degree. Let me make sure. In case it said either said business or non-business. Okay. Received a business degree given that they're female. So I think that's going to be our call right here. So I can, once again, I can just put it anywhere I want. I'll put equals B3 divided by D3. But you can just put the numbers in there. You don't have to do this. I like 152, so I'm going to be 3 decimal places again. Never assume, but it probably is. I've seen them change in the middle of a problem. 0.152. Look at us go. We're tearing this up, aren't we? Okay, that's probably a similar type problem, so I'll just skip that. I remember I said number 7. I didn't look past number 7, but 7. Card problem. 2 cards are selected. The first card is not replaced before the second card is selected, so without replacement. Find the probability of selecting a club and then a diamond. And we're just going to put this in there. I'll put the formula text if you needed to see those again. That way you could pause this up. What's that, B7? So let me look at the problem again. I've already forgot. So without replacement, it's club, then diamond. Okay, we've done that kind of problem. So I probably could have skipped this one, but I'm already committed to it now. Meaning you probably could have figured it out from the notes, but it's obviously not going to take long. Club, 13 out of 52. Times. Now we've lost a card, 51, but the next one's a diamond. It's not back-to-back clubs. So all 13 diamonds are in there. Divided by 51. And then now you can see the command on the left. Hopefully I got this right. If it's 3 again, let's see, 0, 6, 4 if it's 3. Boy, we're just tearing it up here. Let's see. That one doesn't seem to be too bad. Coin is tossed, six-sided die, head, then rolling a number greater than 3. See, those are going to be independent events because obviously the coin flip's not going to affect the die, so the coin will be 1 over 2, and I'll let you figure out what's the probability of rolling a number greater than 3 out of 1 through 6. That shouldn't be too bad. I have complete confidence in you, but obviously you can click the ask my instructor, either to help me solve this first, and there's also from your, I don't know where it is, but the students have a button that says ask my instructor. But sometimes to help me solve this will clue you in enough. So I think we're down to the last one here. That was okay. That one and this one. Let's see. All right. How do I get rid of that stupid thing that says next question? I can't read the number. Well, this is annoying. Oh, there we go. Okay. Oh, I bet you. Let me check all the questions on this one. Oh, okay, it's got a little bit. Well, all right. I'll work with this without redoing it. This is exactly like the type O positive problem I did in the note, so you can refer back to that. So this 10%, 0.1, all three have it, would be 0.1, 0.1, 0.1, multiply them, you get that answer. It wanted 6 decimal places for some weird reason. You see what I'm talking about? You never know what it's going to want. 6, 3, 3. None have it would be, if it's 0.1 that have it, 0.9 won't have it. So it'd be 0.9, 0.9, 0.9. And then at least 1 is the opposite of none. So you see this answer, 0.271, is just 1 minus that answer right there. And this is the only part that I didn't do in the notes, but it's not difficult. The unusual event, meaning less than 0.05, the first one, the event in part A is unusual because it has a probability of 0.05, and then there it is. So that's the unusual thing. So, all right, I think we will conclude this video on conditional probability.